Hello, in this video I'm going to solve the following problem for you. Use the special substitution x equals to tangent theta over 2 to evaluate the following integral. Integral d theta over 2 plus sine theta. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do your calculations correctly, one possible answer that you will get is as follows. 2 over square root of 3 tangent inverse of 2 tangent theta over 2 plus 1 all over square root of 3 plus a constant c. Okay, so now let us solve this integral. So we want to calculate the integral of d theta over 2 plus sine theta. Okay, and they have told us to use this substitution, x to be tangent theta over 2. Okay, so the first thing that we can do is to calculate d theta. So from here, what I can realize is that theta over 2 is tangent inverse of x. So this means that theta is 2 times tangent inverse of x. And then, of course, d theta, I have to differentiate the inverse tangent function, which is 1 over 1 plus x squared. I have a 2 here, so it becomes 2 dx over 1 plus x squared. So this is my d theta. Yes? And now I have to write sine theta in terms of x, because when I do a substitution, I have to get rid of my old variable in favor of my new variable. So this means that I should be able to write sine theta in terms of tangent theta over 2. And we can do it like this. So sine theta can be written as 2 sine half of this angle multiplied by cosine half of this angle. Yes, this is the famous formula for the double angle formula. So this combination is sine of 2 times this angle, which is theta. And then I multiply this by cosine theta over 2 and then divide this. So it becomes 2 sine theta over 2 cosine to the power of 2 theta over 2. To compensate for that change, I have to divide by cosine theta over 2 as well. But this is nothing except tangent theta over 2, and I have a 2 here, so it becomes 2 tangent theta over 2. And this can be brought into the denominator and write it as secant to the power of 2 theta over 2, because 1 over secant squared is just cosine squared. And then we have a famous formula for secant squared of an angle in terms of its tangent squared, and that is equal to, so I copy and paste this part, and then this becomes 1 plus tangent of theta over 2 squared. But now, tangent theta over 2 is x, so this is nothing except 2x, and that is 1 plus x squared. So I realize that sine theta is 2x over 1 plus x squared. So this is sine in terms of x. And now if I call my integral I, so I can use these substitutions to write I equals to integral, instead of d theta, I put this expression over 2 plus, instead of sine theta, I put that expression, and then I multiply the numerator and the denominator by 1 plus x squared. I can also a factor of 2, which cancel that factor of 2, so the integral becomes extremely simple. So the numerator just simply becomes dx. What happens for the denominator? Remember, 2 is gone, and I have multiplied by 1 plus x squared. So this 1 becomes 1 plus x squared, and then I have x there. So if I want to write them in order, I would write x squared first, x second, and 1. So what I did, I just multiplied the numerator and denominator by that. I factored the 2 out, canceled that 2, and then this will go here plus that 1. I wrote them in descending order of the powers of x. Okay, but this is a very standard integral that we are supposed to calculate. That's a second degree polynomial whose discriminant is negative, so I cannot factorize it. So, but I have to make it, I have to extract the complete square out of it. So I will write it as integral dx over x plus 1/2 to the power of 2. What happens? The first one squared is x squared. 2 times the first one times the second one is x. But then this becomes 1 over 4, but my number is 1. So I have to add 3 over 4 to it, yes? So what I did, I wrote this in this form. And then I can introduce a new variable. So let us say that, for example, capital T is introduced to be x plus 1/2. Then, of course, d capital T is just simply dx. So this integral becomes equal to integral. Instead of dx, I just put dt capital. And then here, I can write it as t capital squared. And then instead of 3 over 4, I imagine this is the square root of 3 over 2 squared. But that's a very famous integral. So I write the formula here for you. So integral of d, say, capital X divided by x squared plus a squared. This is a famous arctangent function, so it becomes 1 over a tangent inverse of x over a, of course, plus a constant c. So I want to use this formula by t playing the role of x and square root of 3 over 2 playing the role of a. So it becomes 1 over a, which becomes 2 over square root of 3 tangent inverse of t over this number. T over this number, 2 goes into the numerators, becomes 2 over 2t over square root of 3 plus a constant c. Yes? But now I have to switch back to my original variable theta. So what I will do, I will write 2 over square root of 3 tangent inverse. Yes, I multiply t by 2, so this becomes 2x plus 1. Yes, so it becomes 2x plus 1. Let me do it in 2 steps. And then plus a constant c. But this is not enough because I have to switch back to my original variable. So I have to replace x with tangent theta over 2. So then what happens? It becomes 2 over square root of 3 tangent inverse of 2 times tangent theta over 2 plus 1, and then the whole thing divided by square root of 3, and then I have a constant c. So let me see if that's exactly the answer. Yes, that's exactly the answer we're supposed to reach at. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.